Hello, welcome back. So, in the last video, we were talking about test statistics. So hard to say. Good lord. We were talking about test statistics and how they summarize our data. But unlike the mean, the median, the mode, whatever, we are summarizing our data in the light of the null hypothesis, or with the frame of reference to the null hypothesis, we are summarizing our data. Okay. And then, based on that test statistic, we are able to calculate a p-value. And a p-value, all that is saying is the probability of observing the test statistic or our data, right? Because they both represent the same thing, right? The test statistic represents the data. Our data can be represented as a test statistic, right? So the p-value is the probability of observing our data if the null hypothesis is true. Okay, sort of out there, sort of an abstract idea. How do we assume that this is true? How do we do this mathematically or visually or whatever? Well, I sort of drew it out here. Now, this is exaggerated, very much so, but I think visually this is the best way to see it. So our null hypothesis in our example is that there are, 38% of the birds in northeastern Wyoming are these brown thrashers. We thought otherwise, or the ornithologist thought otherwise, went to go collect data and found that it's actually 34%, or at least based on their sample, they found that the proportion was 34%. And we know that proportions, and we know that sample means and whatever else, they come from a distribution that is approximately normal, right, based on that central limit theorem idea. So what we're doing here in this hypothesis test is we assume that this one here is true. We assume that the null hypothesis is true, and that it comes from some distribution that looks like this. Okay, so we assume that this is true. But then another sort of more casual assumption we make is that, all right, maybe we assume that now my 0.34 that I found, this new data that I found, also comes from a seemingly normal distribution, but we'll treat now this value as the new center. Okay. Now what we want to do is we just want to compare how different these two distributions are, right? How far away they are from each other. And when they get farther away, we are able to then shade the area underneath the two curves, and that's a p-value. Essentially that's a p-value. Now, the further they are away, the less this area will be, right? And you want them to be far away. You want to support your alternative hypothesis. The closer they are together, that means that they are not so much different. Okay. Now, what the heck? What the heck do you do with this p-value? Well, that is a great question. So let's recall that we kind of see this alpha show up every now and again. All alpha represents is this value of 0.05, right? It's kind of like a threshold or like a criteria, right? And all we're saying is that we're cool with our data having a 5% chance of being totally random, right? 5% is pretty small. This is just a relic of the past, too, when we were having to do all this by hand, right? I say we. It was like two dudes that were doing it all by hand, and they just chose this. They chose this value totally arbitrarily, right? It's pretty small. This can be anything, though. Alpha can be anything, and typically it'll be specified, right? But 0.05 is the convention. So, long and short, if the p-value is less than this value, less than 0.05, we reject the null hypothesis. Okay? If it's the other way around, if the p-value is greater than alpha, we fail to reject the null hypothesis. Now, let's take a look at this language, right? Let's take a look at the sort of wordage that is used, right? Rejecting the null hypothesis, makes sense, right? That's at least easy enough to kind of wrap your head around. Failing to reject the null hypothesis gets it's a little convoluted almost. Okay, so in this case, based on our data, we have quite a bit of evidence against the null hypothesis. However, in this case, if the p-value is greater than a, we do not have much evidence against the null hypothesis, right? Based on our data, and in this case right here, we do not have enough evidence against the null, against the status quo. Okay. Now, you might be saying, like, Carson, what the hell? Why do we have to say it like this? Really great question. It's sort of like legal speak, almost, where if you don't say the right thing, then that can be used against you. So, for instance, don't say anything like this, where if the p-value is less than alpha, right, we have significant evidence against the null, right? But we don't say that we accept our null hypothesis. Never, ever, 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 ever use anything like that, because that can be used against you. Because at one point, the null hypothesis was the status quo, right? We just have some evidence against it, suggesting that it might not actually be that. Same thing in the other direction, too. If the p-value is greater than alpha, don't say that you accept the null hypothesis. And this is because you still observed your data, right? You still observed that, whatever it was, the 0.34, right? So what you saw was not, a lie or whatever. It's not like it didn't happen, because it did. It did. We just don't have evidence to suggest that 0.34 is possibly maybe the new norm, okay? So this is the language you want to use, right? This is the language you want to use. All legal speak. Now you're probably saying, what the heck? I don't want to. All right. I totally get it. Now, again, communication is super big in statistics. It's like most of it. In this case, this is probably the best way of communicating, at least conventionally, communicating your findings, right? As far as what your statistics sort of tell you, right? What your test tells you. So in this case, you can copy and paste this all you want. I don't care. Since the p-value was, and then you choose greater than or less than, the chosen alpha of, and then whatever the alpha value was, usually 0.05, okay? So if it is less than alpha, if the p-value is less than alpha, then we say that we reject the null hypothesis that, in this case, brown thrashers make up 38%. And then we say at the chosen alpha level of 0.05 times 100%, right? Just a convoluted way of saying multiply your alpha by 100 to make it a percent. So we would say at the 5% level. So let me sort of give you that whole thing as one big sentence in this case, okay? So since the p-value was less than 0.05, we reject the null hypothesis that brown thrashers make up 38% of the birds in northeastern Wyoming at the 5% level. Okay, this is the statistics talk. Let's put it into English, right? We have significant evidence that suggests that the brown thrashers make up 34% of the birds in northeastern Wyoming. Sorry, I kind of just blacked out there. Okay, so here's what I'm saying. This is the stuff that you'll see in journals, right? This is this optional bit here. I only say it's optional because it's not totally necessary. This is the stuff that puts it back into like English, right? And then after that, you can talk more about how your findings are important and what they suggest, right? If we go on the other end, though, since the p-value was greater than our chosen alpha of 0.05, we failed to reject the null hypothesis that brown thrashers make up 38% of the birds of northeastern Wyoming at the 5% level. There is, and this is the English bit, there is not enough or not significant evidence that suggests otherwise, right? That it's 34%. Okay, whoa. All you want, you can copy and paste this. This is the way to do it, because this won't get you in trouble. and this bit here wraps it all up, I think, fairly nicely, right? This all gets convoluted and not, if you're not very familiar with statistics, which a lot of people aren't, and that's okay. This bit here is universally understood, okay? So, here's a bit of philosophy for you and an actual application in the real world. And I'm going to take a quick sip of coffee here, so I suggest you do the same. Man, all right, I already feel better. Okay, so the first step, this is the real process, right? The first step is develop a hypothesis that challenges the norm. You do that first, and then you collect data. So, like in this instance, the norm was 38% of these birds make up the whole bird population in northeastern Wyoming. That's the norm, right? Maybe I saw less birds when I was, or less of these brown thrashers on my way to work every day, right? that makes me think then that something is up, right? So then I go collect data. Then I collect data. After the data is collected and summarized in whatever way, that's when you figure out, do I even need to do any of this? Do I need to do any of this? If your data and your hypothesis agree, okay? So, and what that means is that if I say, okay, I'm seeing less brown thrashers, I'm going to go collect data and see if it's anything less than 0.38, or if it's anything less than 38%. Based on whatever I find, in this case, I found that it was 34%. That is less than 38%, right? Then I can say, all right, I'm going to do a hypothesis test on this, because now my data and my new data and my hypothesis agree, right? Then I can run a hypothesis test to determine if what I saw was actually just up to chance, or if it might suggest that, there is a new norm. Okay, now, if your data and your hypothesis don't agree, if they are not the same, in this case, it'd be like, I am not seeing very many right now on my way to work. I'm going to go collect data. It turns out that maybe my sample that I collected is actually 50% brown thrashers, right? Bigger than the norm, right? So I thought that, okay, I'm not seeing very many. The population is probably declining, but I collect data that suggests otherwise against both my own hypothesis and the status quo. It's actually larger. That's it. Go home. Your hypothesis was wrong straight out, right? You don't even need to do a hypothesis test on that. Generally, philosophically, as far as statistics go, or at least the sort of mentality of statistics go, you can't switch the direction of your hypothesis after finding the stuff, right? After you're finding your data, because you're just not supposed to do that. Now, can you do that in real life? Sure, whatever. But ideally, that kind of goes against the grain in statistics. Now, you can still do it. You can still do your hypothesis test and maybe suggest otherwise, because the data you found was still, the data you found. No big deal. But we kind of have this idea that if you were wrong flat out at the beginning, don't even worry about it in the end. Okay. One last pro tip, and this will make sense when we get into an example, because I know this is probably long and drawn out and you're probably bored, and I understand. But p-values and tails, right? Let's recall that every distribution has a tail, or at least a normal distribution does. These are the tails, right? Over here and over here. The areas where the probability is slim of something happening, right? What you can do is always do a two-tailed process first. Even if your question is directional, right? If you have a one-tailed test. What you can actually do is just find the p-value of a two-tailed process, right? A two-tailed process, and divide it by 2. Divide it by 2 if you need to have a p-value that is just one-sided, that is directional. And that's it. That's it. So it'll make more sense when we get into it, but essentially what we're doing, I have this drawn out. Let's say I have some test statistic and it shows up over here. What we are doing when we do a two-tailed test is we're saying, what's the probability of that showing up, right? And then what we do, based on our alpha, which is usually 0.05, we cut off 5% of this whole thing, right? So we're now testing what's the probability of it showing up here or here, right? On either end. And then whatever. But if we only want this one side, we're going to get some p-value anyway. If we just want to get rid of this thing, all we need to do, since we got rid of one of the two halves, right? We can just cut that p-value in half, so divide it by 2, and then that's the same thing as doing a one-tailed test. And it's as simple as that as far as the mathematics go. But you're probably wondering, I'm just totally out there, and I understand. This foundation is very important to know the process. It might seem long, it might seem drawn out, but I promise that when we get into an example in the next video, it's going to go by much faster. So I will see you there in just a second.